Okay, so yeah, if you're ready, we'll get started. Yeah.
Yes, yeah.
Okay, so today we're very happy to have Marius Prof from the University of Siegen. He's a PhD student. Is something about his work on human activity recognition, this kind of thing, on video and wearable data.
Yes, I know it's a bit off topic, but maybe you get still some interesting stuff from it. So yeah, thank you for introducing me. Hi everyone. Yes, I'm Marius. I'm from the University of Siegen. The work I'm going to present today is a dataset. So a dataset that we released recently. It's not yet released at a conference, but it's still publicly available, and we're trying to get as much feedback as possible to the dataset. The work was joint work with Christoph von Laufen and Michael Möller, my two doctoral supervisors, as well as Hilde Kühne from the University of Frankfurt, now University of Bonn. All right. Okay, so first a bit about me. So I did my bachelor's in information system at the University of Cologne, then switched to data science during my bachelor's already a bit, and then did my master's in data science at the University of Mannheim. Now I'm a computer scientist PhD student at the University of Siegen. So I have two doctoral supervisors, and I'm expected to finish in 2024, so next year, hopefully, fingers crossed. Some notable things from my studies, which I'm really proud of because it involves me going to abroad, which I tend to really enjoy and loved those experiences. So I did my exchange semester at the University of Seoul in South Korea, was an intern at SAP in Brisbane, Australia, and was a research intern at Yale University for a couple of months. Now, my PhD is interdisciplinary, so I have two doctoral supervisors, Professor Dr. Christoph von Laufen, who is the ubiquitous computing group head at the University of Siegen, as well as Professor Dr. Michael Möller, who some of you might know, who is the head of computer vision at the University of Siegen. So they got together, said we want to have a PhD, and here I am. So double the team meetings, double the fun. All right, so first things first, if people ask, do you release a data set? The first question that you usually get is, yet another data set, do we need another data set? There are plenty out there, what's so special about it? And well, to give you a brief overview first of the current state of inertial and egocentric data sets. So the data set that we released both features inertial data, so sensor data captured from inertial sensors, as well as egocentric vision, so video data captured by the participants. We first wanted to assess the kind of state that I was faced with when I decided to record my own data set. So usually what happens, especially from the vision side, in activity recognition, a lot of those data set only offer trimmed recordings, meaning that the activities are split across clips. Each clip represents a certain activity that someone does. So human activity recognition always is about recognizing what someone is doing at the moment, what that activity is. It can be as much as locomotion, is the person sitting, standing, or is the person, doing a certain step in an experimental protocol. So that's what we're trying to do. We want to tell if someone is doing something at a certain moment. And having those clips is great, but what you are cutting out automatically is all the breaks, the intermediate stuff. So these clips usually don't feature just the activity, but what at least the wearable community is always very much interested in is having a continuous stream. So intermediate breaks, people just not doing a certain task, which is then called the null class. And we want to, of course, have algorithms which are robust against also differentiating in between, is an activity happening of interest or is the person doing something else? The null class problem, it's also the, of course, biggest class then, which is always making this whole problem a really unbalanced problem. And if you do those clips, you're cutting those out. Then, of course, oftentimes, especially the inertial data sets suffer from small participant counts. So not a lot of participants. The thing is with inertial sensors, where it's easier, of course, with video, we need to synchronize the sensors. So the more sensors you have, just the more workload there is actually syncing the sensors and getting a huge data set going. Also, of course, there are these larger vision corpuses. For example, here you can see epic kitchens. So this is a vision data set where people were cooking recipes. and you wanted to recognize the certain step within the recipe, which step is the person currently doing, so is he cutting the onions or whatever. These data sets are usually, because they originate from the vision side, very vision biased, meaning that the activities usually involve a lot of stuff happening in the POV of the person, usually involve a lot of objects, and of course then the inertial modality itself kind of gets just this extra on top, but not really, like the information overlap is huge in that sense, where you can already tell a lot just from the vision side. So, and lastly, well, oftentimes you're also faced with really artificial indoor and artificial sensor setups, meaning there are these data sets where people are equipped with ridiculously amount of sensors. So here you have the Action Sense dataset released in 2022 at NeurIPS, where of course you can see the person's wearing way too much sensors for just cooking. Of course, this is not really real world like. It's cool it's a playground for multimodal activity recognition, yet replicating these setups, extending the data set in the hindsight is just really, really difficult. You need to have all the sensors available, and also these setups then for the surrounding as well, which are equipped with sensors as well. Usually you just set this up once, and then all the participants only participate in one area. So the diversity in recordings is usually less. So everyone's using the same utensils, same kitchen countertop, and so on. So that's why we started an outdoor sports data set, where we said people go outside to do sports, not much equipment, just a sports mat, your sensors, and you basically. We had 18 participants already participate in the study. Of course, this is an ongoing project. We want to have more data coming in, but the current data set state is 18 participants, 10 male, 8 female. We had them do a minimum of 2 workout sessions, meaning you split the 18 workout activities, which are part of the data set, into at least 2 sessions. Of course, it's probably also just too exhausted to do it in one go. Running exercises, stretching exercises, and strength exercises, all kind of having a twist to them. And in the end, we told people, take as much time as you need. Just your level of fitness determines also how many breaks you do, how much time you just take roaming around the experimental setup. And yeah, we left with 15 hours of recording, 615 action segments, so uninterrupted executions of activities at 10 outdoor locations. So you see this was recorded over 5 months. So we have, as you have in Siegen, some sessions where there was snow. I think the worst conditions for a person were -5 degrees during their workout. So a lot of variety, some asphalt ground, like a lot of leaves on the ground during the autumn period. So yeah, this is the current state. Now let's talk about the sensors featured in the dataset. So we thought about using the 2 most prominent sensors which are used during sports recordings, meaning wearable smartwatches as well as action cameras. They're kind of like the 2 most commercialized solutions at the moment, which people are using to track their workouts. We have 4 sensors equipped on the limbs and ankles. So meaning that we're tracking the movement and the acceleration of those body parts, as well as then equipping a GoPro, a head-mounted GoPro on the head, which is tilted a bit such that it captures a large field of view, mostly also then capturing the limbs itself in the setup. Here you can see one of the participants doing burpees. The participants luckily agreed to also include the 3rd person recording for just this setup. The original data set yet does not contain any 3rd person recording to kind of preserve the privacy of the people. We're thinking of maybe introducing some extension, also then media piping the skeleton of the participants and then using that as releasing that where it's then anonymized, of course. But that's just for the future currently, egocentric data and the inertial sensors. Yes. Okay. The activities. There's a large amount of activities. Of course, I'm not going to talk about all of them. You can see me here doing all of them for recording purposes. So that's what also was shown to the people when they were like introduced to what they're supposed to do. So I made these gifts and then showed it to the participants. some things I want to highlight. So first of all, the dataset includes these complex variations, meaning that we took the base activity, so for example, push-ups, and put a twist on it, where in that case, the person was supposed to, while when they're like in the upward position, tap their shoulder and lift their arm to the side, as well as doing this on the other side, of course. So where it's then essential to look at all 4 sensors simultaneously. So it's then difficult, especially differentiating those two activities, really seeing the big picture if you're just looking, for example, at the right wrist, because the right wrist, if you're not looking at this motion of like opening the arms, then look completely the same to normal push-ups for half of the repetitions. Same for sit-ups, some variations and lunges. And you can see, especially in the results, these get a lot of times confused unless you're looking at all sensors simultaneously. Then we have some activities with inactivity sequences. So of course, the longer the activity is, the more difficult it gets just getting the big picture. And you need to then put like some temporal context along the time axis. So for example, burpees itself consists already of a push-up, yet are complemented with this jump. And if you do not see a larger field of view and then or a larger receptive field of your time axis, you would confuse burpees with push-ups and do not get the context that you need to put together jumps as well as push-ups. Same for the lunges complex, we have some sort of stretch to it. So you could confuse it with a stretch in that sense, or confuse just not seeing that these are special lunges. So you need to capture this whole movement one after another to get the full picture. Then, as I said in the beginning, this is not POV focused. Many activities, especially the stretching activities, do not happen usually in the field of view of the participants. So that's where, for example, the inertial side is preferred. Also, jogging, especially, is really sometimes difficult for the vision side to differentiate because it's just slight changes and few frames where you can see, for example, then for the rotating arms, see the arm rotate through the picture. In that sense, then the motion, the optical flow of the video is the same for all jogging exercises. So we're trying to not favor any modality per se and try to make it such that the information overlap across the two, across the inertial side and across the vision side is just as small as possible. All right. Now, before I get into the benchmark results, first of all, what's the current state within those two communities? So we have the inertial community trying to classify inertial data. We have the video community or the vision community trying to classify videos and like spot activities, but what do they actually do? So the current pipeline for inertial activity recognition, what's kind of the state of the art, like the standardized process is we're chunking the data into different windows, meaning that we have the sliding windows shifting over the sensor axis. So in that sense here, this is one sensor. The sensor is capturing 3 axes, so X, Y, and Z acceleration. And we're then grouping together always, in that case, for example, 50 samples, and then shifting this window over the data. And then each window itself is then something we want to predict. So given the data that we see in this window, we want to make some sort of classification on this data. So the windows itself then get passed through some sort of deep learning model. So the kind of like, baseline approach is usually some sort of convolutional plus recurrent network, where the convolution part, of course, extracts some sort of like discriminative features out of the window with the kernels shifting over the inertial data. And then the recurrent part tries to make some sort of like temporal connections within the window. Then what you're left with is per window, you make a classification, you classify, for example, into running, sit-ups, or just the null class, so nothing in that sense. And then you calculate standard classification matrix, accuracy of 1 score, you name it. So those are the inertial people. What the vision people do, or at least the single stage or the temporal action localization community, so specifically in this benchmark analysis, the single stage people, they take video clips. So they're also grouping together frames in that sense and parts of the video into, in that sense, then also you can do it the same way as in the sliding window approach, 1 second clips. So 1 second video clips, and you try to classify those video clips to be some sort of like activity. So what they do is they extract, of course, before they're not working on the raw frames, they're extracting some pre-trained features. For example, I3D features, which are pre-trained on a large vision corpus. They get a feature embedding. The feature embedding gets passed through some sort of deep learning model. And then what's different to the inertial communities, they're not predicting each video clip at a time, but they try to come up with segments, meaning it's triplets, which are then activity, start, and end. So classifying not every record itself, but grouping, of course, together then records and saying, okay, in my video itself, in my 30 minutes of video, from minute 1 to minute 2, the person was running. So it's a classification loss and a regression loss combined. There's a 2 loss optimization going on. And then you're comparing yourself against the ground truth. So how were the actual segments? And I kind of color-coded it here. You're comparing, of course, as far as did you correctly classify the activity. And then it's like in object detection, you're trying to calculate MAP scores rather than classification scores, where you're trying to see, okay, how much overlap do I have with the ground truth? And if it exceeds a certain threshold, you're saying, good job, you recognized the activity. So 2 different communities, 2 different metrics, yet in this benchmark analysis for both types of models, also from both communities, I computed both of them and compared them. How do they end up with the different metrics? Now, one thing which I want to highlight is that we did some early fusion approach using these single stage temporal action localization models, so the vision side. They're using these transformer-based architectures. Well, some of them are not anymore transformer-based layers, yet they're just single-stage models which predict these action segments. And what we notice is that from the data that we start, of course, the current approach, what they're doing is they're working with the camera data first, extracting some sort of feature embedding, then you have a feature vector, which is size in that sense, for example, 2048, where 1024 features are describing what the RGB side of the video tells you what, and then 1024 features tell you what does the flow features tell you, the optical flow. But we can sort of do a similar thing to the inertial data. So learning from what I know from the inertial community, what we did is we took the inertial data, which is then, of course, if you take a window of a video clip, so the video clip has then inertial data across 12 axes in our case. So we have 4 sensors, each has 3 axes, 12 axes. And those 50 samples are then associated with the data that you get from those 12 axes. Well, we can concatenate them, vectorize them in that sense, and then describe the same video clip just using inertial data. So it's a matter of concatenating the axis along the time. So you first have the 50 samples of the first axis, then the 50 samples of the second axis, and so on. And that vector can be used as input also for the single stage TAL models. So of course, also what you can do, which is that multimodal approach, you just combine the 2. So you combine the 2 vectors, feed it into the models, and instead of then working with 2048 features, they work with 600 features or 2648 features. Yes. Now, the training pipeline. So what we use is, of course, 2 different communities, so 2 different types of models. So the first types of models were the inertial activity recognition models. We use the Shadow DeepConf LSTM, which is a model released by us in 2021, as well as the attended discriminant model, which was released the same year, where the DeepConf LSTM is kind of extended a bit with self-attention layers. So kind of, one-upping what the DeepConf LSTM does. For the temporal action localization side, we use 2 very, very prominent models, namely the action form and trident model, which are the current state of the art in their community. They were both released so one of them was released in 2022, and then one of them followed up in 2023 at CVPR. The trident model originates from the action form, yet does some things differently. When they came out, they broke benchmarks significantly. They're single stage models, meaning that you can train the classification as well as regression in one go. So you do not need to have some sort of like anchor windows telling you sort of like suggestions for when the activities start and end. You just do one training and then get the predictions. So those 4 models were then tested. So the inertial activity recognition models were tested in a classic way, 300 epoch stepwise learning rate schedule, and the optimization according to our paper from 2021. Temporal action localization, we used these models both on the vision side as well as inertial side and the combined side just in a plain fashion. So we didn't do any hyperparameter tuning per se. We used the hyperparameters the action former people reported on the Epic Kitchens dataset, which is also an egocentric dataset like us. And we'll just upped the amount of epochs. So increasing it to 300 epochs to also match what the inertial community, the inertial models were trained with. Now, the model itself was validated all models were validated in a pre-split cross-validation, meaning that you're always validating on data which is originating from unseen subjects. So you're not overfitting on certain habits that people have in executing their activities. Of course, every human has its own movements, own gait, and so on. So we want to make our algorithms robust against overfitting on these things and get how good is our model at predicting unseen data of unseen humans. We did this 3 times for each algorithm, so meaning that we are varying the random seed. And for post-processing, so what happens with the inertial side is they're predicting each window individually, so they're not really predicting coherent segments. What happens is it's really scattered. It's a really scattered timeline where it can be that there are one-off predictions where the model thought it was a different activity. So we're kind of cleaning up this mess by running a majority filter after having the predictions over the prediction timeline, only taking the majority label. In that sense, the 15-second filter there proved to be most effective, where it's then happening that these one-off false predictions just get overwritten with the majority label, and we get more coherent segment, upping the MAP score. For the temporal side, the vision side, or the vision models, we used score thresholding, where if you don't do any score thresholding, what happens is every timestamp in time gets classified, and things like the null class just get disregarded, meaning that, yeah, you're not classifying there to be any breaks, and every timestamp, no matter the confidence of the model, just get classified somehow. So thresholding the segments at 0.2, meaning that only segments where the model was at least 0.2 confident in score were considered to be actually predictions. Others were thrown away, meaning that they automatically become the null class. Now, results-wise, so here you can see on the bar chart, we have the inertial side, so using only inertial data as input. We have the camera side, so using only the videos as input. For the inertial side, we tested all 4 models using the trick that I earlier mentioned. And we can see that, especially as far as F1 score, the models, though originated from a different community, actually are quite competitive as far as F1 score than the models which were originally developed for that modality. And what's of course great is, because they are trained for it, they have a regression loss being trained there. The segments are way more coherent, and the MAP scores are way higher for these vision-based models. Of course, they're training more in a retrospective manner, where we're considering always the video happened and we try to classify the complete timeline, whereas the inertial side always makes this one-off predictions. Give me a window and I make you a prediction for it. So you can use this more, of course, in an online approach. Yet, of course, sometimes it might be very important to have better coherent segments, better predicted segments with start and end times. On the camera side, we can see they're a bit worse. So meaning we're already very challenging on the camera side. Of course, the benchmark analysis are not a picture perfect validation. There's of course a lot of optimization effort can be invested into both models, both sides. Yet Once we combine the two, we can see that we're increasing the F1 score of the temporal action localization model significantly. We're rising in F1 score up to 80% for both models, 81% for the TriDot model, and the MAP score even more significantly rises, meaning that learning combined from both modalities holds some sort of value, which does not come close to when you're just looking at one modality at a time and then combining it in the end. And to stress this even more, first, let's look at the actual predictions. So I know this might be a bit hard to see. Yes, the color coding tells you, of course, where the predictions in the confusion matrix are better in that sense. So darker green means more predicted correct cases on the diagonal. Yeah, we can see, first of all, for the inertial side, it really struggles with differentiating the null class from the activities. So there's a lot of confusion amongst just the activities itself and the breaks, probably also the start and end times. And so the TriDot model struggles there. And also some of the complex variations get confused on the inertial side, where, yeah, it's just these twists make it difficult to differentiate those activities. On the camera side, you can see that especially the jogging exercise really confused a lot amongst each other, meaning that, of course, there it's important to find some sort of way how to really stress what's important, how to differentiate those. But what we can see, of course, if we're combining the two, the strength of both modalities, at least for the TriDot model, get combined. And in general, we can see an increase of all activities, and the kind of weaknesses of each model get eliminated and substituted with the strengths of the other model. Now, last thing I want to talk about is the oracle approach. So further digging deeper into what do the different models do best, and also how much is the loss of the two or the predictions of the two correlating. We wanted to see, well, what happens if we're combining the two predictions. So two single modality models, inertial and the camera, what happens if we're combining them? And we want to combine them in a perfect fashion. So a setup which is unrealistic from a real world perspective. So we're always just picking the correct label of the two. So combining the two prediction streams and having this oracle which tells us which one is the correct one, if there is a correct one. So the first oracle we tested, what happens if we combine the single modality models? We can see, sorry about that. We can see that the, so this is the gray crossed out bar. We can see that the F1 score significantly increases, meaning that the models learned different things, that learned to predict different activities, different instances of activities correctly. So if you combine the two, you can see with 93%, in general, one of the models is usually right, yet, of course, there needs to be some sort of consistent and correct way to combine the two. Yet, what we also saw is that the MAP scores of the multimodal models, so the blue one, are higher than combining in a perfect manner the single modality ones, meaning that in that sense, the multimodal model learned to predict activities or like activity boundaries more consistently, looking at all the modalities simultaneously rather than just looking at one and then learning from one of them. And this is especially then prominent if we're combining the single modality models with the multimodal model. We see that there's still an increase in F1 score, meaning that the multimodal learned to classify instances correctly, which were previously not correctly predicted, and the MAP score just rising even more significantly to 81%, where it was previously stuck at 72%. So a lot of the boundaries just get way better predicted when using multimodal data than using single modality data. Okay, now takeaway messages. We introduced where 18 participants, 18 different workout activities, 15 hours of data, 10 outdoor locations. So we're hoping to just serve two communities with this data set, see what people think of. We already heard like a lot of ideas as far as correct execution of activities, repetition count, So of course, sports activities offer a good playground to just try out different modality combination techniques, but also just application scenarios. And we're providing untrimmed inertial and camera data of these workouts. So in a sense, if you want to do some workout recognition, it's just a more realistic setup where the breaks are not cut out and we actually see the complete picture of a workout of a person. It's easy to replicate. It's a real-world setup. We're featuring only sensors which are used in commercialized solutions, or the most prominent sensors. And there's a potential to be extended. So we have plans to include new participants, new re-recordings, so re-recording people during different times of the year, at different locations, and of course, maybe seeing if there's some sort of improvement as far as when are people recorded, is there learning effects and such. So in that sense, sky's the limit for a data set. We're already at 18 participants, but of course, it's easy to extend it. Who knows to where? We benchmarked two vision-based architectures, which are kind of state-of-the-art in their respective areas. We proved the versatility of the vision-based approaches to fuse both modalities, but also to work on a previously completely unknown modality for the two. And we had the multimodal approach, again, producing the highest MAP scores and close to best of one scores, showing that multimodal learning is important. And the Oracle approach indicated this, that just the data set is also far from being saturated. There needs to be more, like, better ways to combine the two modalities. And with that, I'm going to leave you. And yeah, where's an ongoing project? I put you the link there to the data sets, to the QR code. If you'd like to contribute in any way, of course, it's maybe not in this setup, but feel free to reach out if you want to use it somehow. I'm happy to also hear feedback about what to maybe change about the data set for future recordings. And just as a cheeky side note, I'm looking for internships. So if you know someone who knows someone, let me know. I'm happy to discuss. And yeah, that concludes my presentation, and thank you all for your attention.